The RF propagation visualizer is a tool that can help network planners plan their future cellular networks much more effectively by visualizing RF propagations on a three-dimensional scale. Now, South Africa has a lot of natural resources, coal, platinum, gold, just to name a few. But there's one resource that we have which is currently very underutilized, and that is our RF spectrum. And as with any natural resource, if we misuse it or use it inefficiently, then future supply just cannot keep up with the demand. So what's a possible cause for this inefficiency of allocation? Well, we identified poor cellular network planning. Now, prior 5G developments, network planners plan their networks by using a two-dimensional top-down planning structure where transmissions are visualized in a two-dimensional scale. But 5G, especially with UAVs and other such technologies, made it apparent to rather visualize propagations in a three-dimensional sense. And this is where the RFPV comes into play. Now, the RFPV is a software package written for Windows devices in Unreal Engine and C++ to do exactly that. Quick solution overview. Now, the RFPV consists of 5 subsystems. Firstly, the visualization environment, detailing the ArcGIS SDK for game engines to render realistic terrain. The elevation extraction model was developed to extract height values from HDT files, which forms part of the SRTM digital elevation model. The propagation modeling subsystem was developed for signal strength prediction through the use of free space, Okumura-Hata, and the Longley-Rice model. The navigation model is responsible for relating game engine coordinates to the global coordinate system, which is the real-life coordinates. And then the user input control subsystem is responsible for any user input. So let's say, for instance, we are a new network operator here in South Africa, and we got permission to put one of our first broadcast towers on the top of Devil's Peak in Cape Town. And we want to map out how the coverage will look for the greater Cape Town area. So here is the beautiful environment rendered through the use of the ArcGIS SDK. Let's say, for instance, we want to know the propagation pattern utilizing the Okumura-Hata model. Various input parameters can be changed here in this input panel. Let's just change our raster length, which corresponds to the size of the visualization, and the resolution corresponding to the accuracy. If we were then to visualize our input configuration, visualization such as the one you are seeing now is presented. Now, colors ranging from red to blue correspond to strong and weak signals. Strong is here minus 30 dBm, weak minus 110 dBm. And as we can see, the signal propagates quite quickly towards a very weak signal, and this is because we initiated a suburban area utilizing the Okumura-Hata model. But as such, there's still signal present here in the areas underneath Devil's Peak, which is not actually in line of sight with the antenna. So let's propagate, or let's visualize that with a more accurate model, the irregular terrain model. We can also then change a lot of its input parameters here. Let's say, for instance, surface reflectivity. We would like to visualize it for 320 in units configuration. For the same 1.2 gigahertz signal, if we visualize our configuration now, we can clearly see the presence of some coverage holes, which I think is quite cool. Again, red is our strongest signals, and there's the existence of some coverage holes here underneath. As our character moves through the world, we can clearly see our signal strength based on the chosen propagation model indicated below, as well as our path loss, as well as our altitude above sea level, which is extracted from the HGT SRTM dataset from NASA, and our live location as we navigate through the world.